This is week 12, part 6, positive lenses. So, positive lenses are the ones that tend to focus a beam of parallel light. Well, they focus any light. They bring the rays together. So these rays would focus in and come to a point right about there. And we call that the focal point. If it's parallel rays in, they go to the focal point, F. And the distance from that point to where the lens is, we call the focal length. This works both ways. Here I've got parallel rays coming in, and they focus to a point. We could also have an example of rays coming from a point and going out parallel. And that is also the focal point of the lens. There are two focal points, one on each side of the lens, and you can label those points in space even if you don't have rays going through them. So these are the focal points, and they're the same distance away. The focal length is the same on both sides of the lens. That's the focal length. That's what characterizes a lens. We can also speak of the power of the lens. It's just a different way of characterizing the very same property. And the power of a lens is just 1 over the focal length. If the focal length, the focal length normally is given in centimeters or millimeters, but for the purposes of calculating a power, you must change it to meters, so that the units then would become 1 over meters, and that is the same thing as diopters. A diopter is an inverse meter. So you can characterize a lens by its power in diopters or its focal length in centimeters or millimeters or whatever you want to give it in. Lenses can have different focal lengths, different powers. We could have a lens that is more gently curved, and in that case, these parallel rays coming in would focus much further away. And so we might have a picture that looks more like that, where the focal length now is longer and the power would be less. So this would be a longer focal length, a lower power, and the lens would be less curved, less strongly curved. To get a short focal length, you have to have a real fat lens in the middle and real thin at the edges, so it's curved very sharply to get that effect. Now let's take a look at this picture that I have shown you before. We can look at a couple of particular rays and see what's going on with this focal point here. Notice I've labeled them on here. They've been here the whole time. But notice that the rays that are coming in here, this red ray across the top, is parallel to the optical axis. And so it ends up bending and going right through the focal point. Down here, this blue ray is parallel, and it goes right through the focal point. Of course, the optical axis is parallel to the optical axis, and it goes right through the focal point too. So those all converge right on the focal point. In the midst of all this other stuff that's going on, that's still happening. All the rays that come in parallel go through the focal point. By the same token, the rays that go through this focal point come out parallel. It doesn't look quite perfect, but this blue ray here coming along through the focal point comes out parallel. Here's a red ray, comes out parallel. It looks like it's off just a tiny bit. So that just shows you again, rays that happen to go through this focal point, hit the lens, they will come out going parallel. Now, what about the object and image distances? That's the thing that we're going to be working with a lot to try to figure out where images form. So certainly you put a candle here and you get an image over here. Can we calculate the distance for that image? This can vary in all kinds of ways, but there's a very simple formula that tells us what's going on. And it doesn't have a real good name. I think we'll just call it the object and image formula. I've not heard another better name for it than that. And it's simply that if we have a situation, let's draw a nice lens here and an optical axis and put our focal points on here. Here's a lens that's got a focal point there, but we'll put an object out here somewhere. That's a parallel ray, so it's going to go through here. Here's a ray right through the middle. And then we'll put a ray down at the bottom here. And it looks like we're going to have an image form right about there. Can we calculate that somehow? This is sort of our stereotypical case where we've got these focal points, we've got a positive lens, we've got an image sitting in the usual place. The way we define the distances is by labeling how far away the object, here's the object, how far away the object is from the lens, and how far away the image is from the lens. And I'm going to use S object and S image for those distances. Object and image, O and I. And the formula is simply that 1 over SO plus 1 over SI equals 1 over F. That's the basic formula that we're going to be using. And this case that I've drawn right here is the sort of stereotypical one in which all of those numbers are positive. Now, let's just take a look on a different screen here, where I can show you how this behaves. Now, if you look at what's going on here, you can see the object and image move around. And as I bring the object closer to the focal point, the image moves further away. If I make the object go further away from the focal point, the image gets closer to the focal point. What happens if I move the object right to the focal point so that its distance is the focal length? Now what do you see? Look at these rays on this side and you see it doesn't look like they're going to converge anywhere. In fact, they all look parallel. What would the distance be in that case? Well, it's gone away to very, very far away. In fact, we might say that's infinite. So that's an image distance of infinity in that case. What if we keep going and move even closer? Now, these rays are diverging, and the image doesn't form out there. There's an image that forms on the other side, and we call that a virtual image. These rays look like they're coming from over here, and the image distance would be from the lens to this point, but that distance would be a negative distance. So we'd say that S sub I is negative. Okay, let's come back to our formulas again and talk about one other feature here. Another thing that we often want to figure out is how large the image is. What is the magnification? So let's draw this case one more time. So here's our lens, and we'll put an object out here somewhere. And this time I want to focus on how big is the image. So I'm not going to draw the other rays. I'm just going to say there's an image over here somewhere. And there's one ray that goes right through the middle of the lens and doesn't bend at all. And over here is the object distance, and here is the image distance. And the first thing I notice is the image is upside down, but what I'd like to know is how big is it? So I'm going to define the height of the object as HO, and the height of the image is going to be h sub I, except I want this h sub I to include whether it's upside down or not. So in this case, I would say h sub I is negative. We will define the magnification in this case to be the image divided by the object height. So in this case, since it's upside down and h sub I is negative, the magnification would be negative. That's the way we would expect. So a negative magnification. So if m is negative, that means it's upside down. Now, how do we calculate that, though? That's a nice definition for what we mean by magnification. How big is the image compared to the object? But how do we calculate it? Say we set up a lens and we'd like to know what is the magnification. The way we can do that is by looking at the two triangles that I've drawn up here. And you realize that they are similar triangles. They share this angle. That angle is the same in both cases. So if those are similar triangles, we can make ratios all over the place. Any kind of ratio you like will work. And so if you look at HI over HO, which is what we mean by magnification, that would be the same thing as SI over SO, except for one difference. And that is h sub I, we intend to be a negative number to express the fact that this is upside down. But s sub I is not negative. S sub I is the image distance on here, and we consider that positive. So to make this relationship work, we have to put in a minus sign right there. So right there, you can see a new simple formula for calculating the magnification is minus the image distance divided by the object distance. So this is how we define magnification. It's what we mean by magnification. This is how you often will calculate it in a problem. Let's work an example to make all of this a little bit more clear and concrete. So let's say that we have a lens out here, and we'll say that we happen to know that it has a focal length of 25 centimeters. So that means it's got these focal points 25 centimeters away on either side. And what we're going to do is we're going to put a pencil out here. And the pencil is 8 centimeters tall. And I haven't drawn this to scale, but we're going to have the pencil be 60 centimeters away from the lens. And the question is, well, there's a whole bunch of questions we could ask. Let's ask, for example, what is the power of the lens? What is the power of the lens? Well, if the focal length is 25 centimeters, the power is 1 over f. You'd be tempted to just take 1 over 25, but remember, to get the power properly into diopters, you must express the focal length in meters. So this would be 1 over 0.25, and that's 4 diopters. Diopters, by the way, are the numbers that an optometrist uses. When you talk about the prescription for your glasses, those numbers are in diopters. So that's the first question. Now, another question might be, where is the image? Where would we find the image? We want to put a piece of paper in here to see an image of the pencil. Where do we put it? How do we calculate that? Well, that takes this usual formula for object and image distance. 1 over s object plus 1 over s image equals 1 over f. So to put the numbers in, we'd have 1 over 60 centimeters plus 1 over the image distance equals 1 over 25. Now in this case, as long as you put S, O, SI, and F in the same units, you can use any units at all. Inches would work just fine. But we'll just keep it all in centimeters, and we'll get our answer in centimeters that way. So 1 over S sub I is going to be 1/25 minus 1/60. And if you work that out, S sub I turns out to be about 43 centimeters. So the image will be located, we could put our, if that's 60, then where is 25? That would be 30, a little less than that. So there's a focal point, and here's a focal point. The vertical distance isn't to scale, but the rest of this can be. 25, and now we've gone out almost twice that far. So out about here would be our image. 43 centimeters. Now let's ask, what type of image is that? What type of image? Well, you can guess that it's upside down or inverted. It just is. When you're doing a case like this, it will be inverted. We'll see that in the formula for magnification in a moment. We'll still get a minus sign there. It's inverted. And the other question is whether it is a real or virtual image. And the distinction there is, do the rays really go through the place where the image is? And in this case, yes, these rays will be focused down through a point like that and so on. These rays will really, in fact, be going through that point. If you put a piece of paper there, it would show that image. So this is, in fact, a real image. It's a real image. It's an inverted image. That's what kind of image it is. So what magnification do we have? Okay. Can we figure out what the magnification is? Well, for that, we use this new formula that we just got, and that's going to be S sub I over S sub O. Remember to keep that minus sign in the formula. And S sub I we just calculated was 43 centimeters, and SO is 60 centimeters. And that gives us an answer of minus 0.72. So the minus sign tells us it's upside down. The fact that it's less than 1 means that it's going to be a smaller image than the object was. If it was exactly 1, they'd be the same size. If it was 2, then it would be twice as large. That's the magnification. So how large is the image? It says the object here is 8 centimeters. So how big is the image? And that just comes from our definition of magnification. Magnification is h of the object, h of the image divided by h of the object. And we're trying to figure out how big is the image. So h sub I is equal to HO times M. The object is 8 centimeters, and our magnification is minus 0.72. And so we're going to get an image size of minus 5.7 centimeters. Minus, again, meaning it's upside down, and 5.7 tells us it's a little bit smaller.